Hello everyone, welcome back to the playlist of numerical methods. In this video, we are going to understand what is trapezoidal and Simpson's rules. These two methods are part of numerical integration. First of all, let us understand what is need of the numerical integration. If I ask you to find the integration of e to the power x dx, it is very easy for you to find the integration. Similarly, if I ask you to find the integration of a polynomial x square plus 2x, it is still easy. If you want to find the integration of any trigonometric function, it is still easy. But what if I want you to find out the integration of e to the power x square dx, sine of x square, or sine x by x, or the integration of log x. You cannot find the integration of these terms, but still we want to find the area under these curves. Finding an exact integral in these cases is extremely difficult or impossible using traditional analytical methods. This is where numerical integration steps in to offer a practical solution. When we talk about numerical integration, we are essentially trying to approximate the integral of a function instead of relying on calculus to give us an exact result. We break the problem down into manageable pieces and sum up those parts. Two of the most widely used methods for this are the trapezoidal rule and Simpson's rule. Suppose I want to find the integration of a function f of x from a to b, and let the graph of this function be this, where this is my point x naught, this is x naught plus h, this is x naught plus 2h. Similarly, going on, the last point will be x naught plus n times h, and the corresponding points on the function will be y naught, y1, y2, yn minus 1, and lastly yn. The point x naught is nothing but initial point A and this last point B. And we have divided this whole interval in n equal parts, and we can write it as this function f takes the values y0, y1, y2, so on to yn for the x values as x0, x1, x2, so on to xn. And let us divide the given interval a comma b into n sub intervals of width h so that x naught is equals to a, x1 is equals to x0 plus h, x2 is equals to x0 plus 2 times h, and so on to xn is equals to x0 plus n times h, which is equals to b. Then the integration value can be rewritten in the form of x0 plus nh x0 f of x into dx. Putting x as x0 plus r times h, differentiating both sides, this will be equals to h times dr. So the integration I will become h into integration of 0 to n f of x0 plus r h dr. Let us remind a concept we have discussed earlier in our videos, named as Newton's forward interpolation formula. Let me rewrite this. In that, we suppose the function f has tabulated at some n plus 1 equidistant points, and the corresponding value of the function f of x are given. Then we approximate this function f of x by some polynomial named as phi n x. We can further simplify this polynomial by taking x as x0 plus p times h, implies x minus x0 value will be p times h, which can be replaced in this, and for x minus x1, which can be rewritten in the form of x minus x0 minus x1 minus x0, and the value of x minus x0 has already been calculated as p into h, and the distance between x1 minus x0 will again be h. So this value will be h times p minus 1, which will be replaced in the place of x minus 1 in phi of n. Similarly, x minus x2 will be x minus x1 minus x2 minus x1, where x minus x1 is already been calculated as h into p minus 1. This will be again h. So the final will be h into p minus 2, which will be replaced in the place of x minus 2 in phi n. Therefore, the updated phi n x can be written in the form of y0 plus forward difference y0 by h into ph plus second forward difference upon 2 factorial into h square p into p minus 1 into h square plus third forward upon 3 factorial h cube into h cube p into p minus 1 into p minus 2, so on to. We can also cancel the h here. So the final equation will look like this. This was just the recap that we have needed in this lecture. If you have found this thing difficult to understand, then do visit the lecture video made on this method where I have explained each and every step of it. Link to that video is added in the description. The main motive to introduce Newton's forward interpolation formula here was to make an understanding that this method helps us to approximate the given function f using some tabulated set of points. Till now, we had a function f of x and we were interested to find the integration of that function, which was not easily possible. So what we did, we break that interval a comma b into n equidistant points and finally came to the equation number 1. Now I will use this Newton's forward interpolation formula to approximate this polynomial. So the integration will become I is equals to h into integration 0 to n f of x naught plus r times h into dr. This will be equals to h time integration from 0 to n y naught plus r times forward difference y naught plus second forward difference upon 2 factorial into r minus 1 plus third forward difference upon 3 factorial into r minus 1 into r minus 2 and so on still. Now integrating term by term, we obtain integration from x naught to x naught plus n times h f of x dx is equals to n times h y naught plus n by 2 times forward difference y naught plus n into 2n minus 3 divided by 12 into second forward plus n into n minus 2 square divided by 24 into third forward difference and plus so on still. From this general formula, we will deduce the important quadrature rules by taking the values of n equals to 1, 2, 3 and so on. And this method is known as Newton's cotes quadrature. The first form we will discuss is trapezoidal rule. Let us mark this as star, putting n equals to 1 in equation star and taking the curve through x naught, y naught and x1, y1 only, that is a polynomial of first order, so that differences of order higher than first become zero. Graphically, we take only this portion to approximate the integration. This will be done by joining a straight line from point y0 to y1. Since we have to put n equals to 1 in equation star, so that equation will change into x0 plus h f of x dx is equals to h times y0 plus first forward difference upon 2. Rest of all the terms will be 0, and we can write this in the form of h by 2 into y0 plus y1, because we know the value of first forward difference is equals to y1 minus y0. This is known as trapezoidal rule. Similarly, if we will find the integration from x0 plus h to x0 plus 2h f of x dx, this will become h times y1 plus first forward difference of y1 divided by 2. This will become h by 2 into y1 plus y2. Similarly, going on, generally we can say integration from x0 plus n minus 1 h to x0 plus n times h f of x dx. This will be h by 2 into y n minus 1 plus y n. What have we actually done is, this part will calculate the area under the curve, and this part will calculate the area under the curve from point x1 to x2. Similarly, the rest of the parts will be calculated, and in the last, this part is calculating the area under the curve between xn minus 1 and xn point. To find the area under the curve from point A to B, we have to add them all. So adding these n integrals, we obtain integration from x0 to x0 plus n times h f of x dx, which is equals to h by 2 into y0 plus 2 times rest of the terms except yn. This is known as composite trapezoidal rule. Understand that if we are finding the area of each strip separately, then it is known as trapezoidal, and if we are finding the area under the curve from the point A to point B, which is approximately equal to the sum of the areas of all the n trapezoidals, which is known as composite trapezoidal rule. One strip, only trapezoidal rule. Sum of all the strips, composite trapezoidal rule. Till now, I hope trapezoidal rule is clear to you. Now we will move to Simpson's 1/3 rule. In trapezoidal, we had put n is equals to 1, but in Simpson's 1/3 rule we will put n is equals to 2 in equation star. In trapezoidal we have considered only one strip at a time, but in Simpson's 1/3 rule we will consider two strips at a time. The integration x naught to x naught plus 2 times h, as we have used the value of n as 2. This will become 2 times h into y naught plus first forward difference plus 1 by 6 into second forward difference, which will be equals to h by 3 into y naught plus 4 times y1 plus y2. This is my Simpson's 1/3 rule. But similarly, we can find the integration value from x naught plus 2h to x naught plus 4h, which will be equals to h by 3 into y2 plus 4 times y3 plus y4, and so on to integration from x naught plus n minus 2 times h to x naught plus nh f of x dx will be equals to h by 3 into y n minus 2 plus 4 times y n minus 1 plus yn, where n will be even. Adding all these integrals, we have integration from x naught to x naught plus nh f of x dx is equals to h by 3 into y naught plus 4 times odd terms of yn till n minus 1 and 2 times even terms till n minus 2, and lastly yn. Since we are already given that n will be even. Why? Because we will be dividing our interval with respect to two strips collectively. So n must be even here, otherwise we will be left with a single strip. And when n is even, automatically n minus 1 will be odd and n minus 2 will be even. This is known as composite Simpson's rule. I am repeating again. While using Simpson's 1/3 rule, the given interval must be divided in even number of equal sub-intervals, since we have to find the area of two strips at a time. I hope you have made an understanding of these methods. We will try to do some practice questions in the next video. If you still have any doubts regarding this theory, then do let me know in the comment sections. And if my efforts are helping you, then show some love to my videos and share it to your friends. Happy learning!